The busiest shipping lane in the world sits above a railway tunnel. Between Britain and France, the undersea section alone runs for about 23.5 miles. On a map, it looked easy. Underground, it was a trap. One wrong move, and water could enter the excavation. Another wrong move, and clay could lock the machine underground. The tunnel had to stay inside one rock layer, only about 65 feet thick. At its deepest point, it ran about 250 feet below sea level.
So the real challenge? It wasn't just crossing the channel. It was surviving the ground beneath it.
For 200 years, engineers wanted a fixed link across the channel. In 1802, one plan imagined horses moving through a tunnel lit by oil lamps. In 1880, they actually started digging. Then fear, money, war, and water stopped it again. The distance was short. The risk was enormous. After failed starts, Britain and France finally agreed to build it. But one tunnel was never enough. They built three: two rail tunnels for trains, one smaller service tunnel for survival.
The middle tunnel was smaller, but in a fire, it became the most important space in the entire project.
Now both countries had to start digging toward each other. On the French side, the village of Sangatte became ground zero. Engineers built a circular launch shaft about 215 feet deep. In England, the problem was different: a vertical cliff face. They blasted and removed more than 300,000 cubic yards of rock just to create a flat base.
Before they could build the tunnel, they had to build the place where tunneling could even begin.
Then came the real enemy: geology. The root had to stay inside chalk marl, strong enough to hold shape, soft enough to cut, and mostly watertight. Too high, and the machines could hit porous rock. Then water became the enemy. Too low, and clay could seize the cutter head. The safe path was not just a tunnel line. It was a narrow target under the sea.
They were not just digging forward. They were trying not to leave the only layer that could protect them.
Years of seafloor drilling and rock testing narrowed the route. Then came the tunnel boring machines. 11 machines were built, 6 launched from Britain, 5 from France. Together, they weighed around 13,000 tons. Each machine was not a drill. It was a moving underground factory. The cutter head alone could weigh about 660 tons. It cut rock, removed spoil, pushed forward, and built the tunnel wall at the same time. Every concrete segment became a wall between the workers and the ocean.
That wall was not decoration. It was the line between a work site and the sea.
The British side was drier. The French side was wetter, looser, and more dangerous. That is why the French machines use sealed faces and pressure control. Inside the unventilated headings, temperatures could climb toward 122 degrees Fahrenheit. Heat, dust, pressure machinery, miles from daylight. The service tunnel went first. Every foot tested the ground before the larger rail tunnels followed. Crews watched for water seepage, a stain, a wet joint, a slow leak. A small water path could become a flood. A flood could trap an entire machine crew.
Down there, a leak was not a maintenance issue. It was a warning.
To stay inside the chalk marl, they needed absolute precision. Lasers helped, but the real guide was a gyroscopic guidance system underground. Operators steered 1,000-ton machines through rock they could not see. And somewhere ahead, another machine was coming from another country. One wrong angle, and they would miss in the dark. Then came a different problem: the dirt. Nearly 10 million cubic yards of material had to be removed. On the British side, chalk spoil was pushed toward the coast. It created about 74 acres of new land at Samphire Hoe.
They dug under the channel and used the waste to push the coastline outward.
After about 24 miles, the service tunnel faces were only a few yards apart. Two separate worlds were drilling blind toward one point. Then came the pilot hole. On December 1st, 1990, British and French workers reached each other beneath the sea.
Hello, my friend.
The final alignment error was less than 2 feet.
24 miles apart, 250 feet under the sea. And after all that, less than 2 feet.
But then the machines became the next problem. Some British tunnel boring machines were too large to turn around or bring back. To save time, they stripped them, sealed them, and buried them under the channel. A 1,000-ton tool became part of the ground it helped conquer. The tunnels still needed air, power, signals, track, and safety. Giant fans had to push fresh air through the system. Power cables fed 25,000-volt electric trains. And every train pushed a wall of air ahead of it.
This was not just a hole through rock. It was a pressure-controlled railway system.
But the greatest fear was fire. About every 1,200 feet, passengers had an escape route into the service tunnel. Detection, suppression, lighting, ventilation, communication, and evacuation had to work as one system. The engineering was extraordinary. The finances were brutal. The cost grew from about £4.7 billion to about £9.5 billion. And the human cost was real. 10 workers died during construction. In May 1994, the Channel Tunnel opened for business. But the real test came 2 years later. A fire broke out on a heavy truck shuttle train fed by vehicles, tires, and cargo. The service tunnel became the refuge. The escape design saved lives.
That fire proved why the third tunnel existed. It was not extra space. It was the lifeline.
Cars, trucks, passengers, freight, and trains could cross the sea without touching the water. Later, High Speed 1 cut the London to Paris trip to about 2 hours and 15 minutes. For centuries, the channel was a barrier. Then engineers turned the barrier into a connection. They did not defeat the sea by ignoring it. They defeated it by designing around every way it could kill the project.
They didn't cross the sea. They went under it. Subscribe to How Cities Function for more fascinating infrastructure videos.